Okay, so we will be recording this part of the session. If anybody has any objections with recording, please say so now. We are doing backgrounds, Zoom backgrounds today. So I've got my bat signal background. That's in honor of our upcoming addition to the family, baby JD, as I'm going to be calling him from now on. And JD means Jorge Damian. And again, yes, Damien is because we're naming him Damien because of Batman's son, Damian Wayne. Okay. We were talking about last class. We're in the unit that has to do with electricity and magnetism, and the cool thing about this unit is that it has a bunch of name dropping in this unit, meaning that there's a bunch of laws and effects that are related to electricity and magnetism and its phenomena. And we were talking about the Hall effect, and we were talking about Hall effect sensors that basically use the Hall effect to be able to detect different things, which is basically we are detecting a variation in the magnetic field. So the Hall effect, as we were talking, quick summary, if we have any sort of thin film that's a conductor and we apply a current through that film, that conducting film, the elements or the electrons, the carriers are going to align themselves. And we immerse it, in a magnetic field. The particles are going to align, and there's going to be a voltage that's perpendicular to the movement of the current, and that's called the Hall voltage. If we move the magnetic field or change any of the parameters, the current, the material, the thickness, or the magnetic field, we're going to see a change in the Hall effect. So if we have this thin element and we move the magnetic field or move the element, then we're going to see a change in the Hall voltage. And this application is used for sensors and for many applications, automotive safety, has seen their appliances, fluid monitoring, and even for automation building. There's easy ways to do switches using the Hall sensor principles. And so we had seen a video where we'd seen the movement of a motor and turning on or off of a LED with using this Hall effect. That's what we were talking about previously. I'm drinking cold coffee in my, oh, you can't see that because of the virtual background. It's the Bat family. It's the Bat family cup. The Bat family. My wife is Batwoman, not Batgirl. There's Batwoman and Batgirl. My wife was Batwoman in that. How do you differentiate? How do you differentiate Batwoman from Batgirl? In the uniform, Batwoman's logo is a red bat, mostly. And it's her theme is usually red and black. Batgirl is usually purplish, yellow, and black. And so that's the difference there. And I think baby Sarah was actually Batgirl there, and I was obviously Batman. Okay, now let's do some more name dropping. So we're going to be talking about a bunch of other people here, 3 people here, that have to do with electromagnetism. And some of you did plays regarding the lives of these folks. So first, and by the way, not to minimalize things, but really, we're talking about the same thing. We're talking about the same thing, but actually in different perspectives and different mathematical statements. But remember what we were talking about before. Everything is really based on this. Everything is really based on this. If I have a conductor, so if I have a conductor where current is moving through the conductor, there's going to be a magnetic field. That's the first right-hand rule. There's going to be a magnetic field. If I have a current going through a conductor and I have a magnetic field where that is immersed, there's going to be a force. And if I have a magnetic field and a particle moving through that magnetic field, there's going to be a force in it. So we're going to be talking about the same thing over and over and over. Remember that. Conductor that has a current going through it, magnetic field. Conductor that has a current going through it, placed in a magnetic field, there's going to be a force. And there's going to be an electromagnetic force, an EMF, a voltage. Also, that's the Hall effect. Magnetic field, something that is charged moving through that magnetic field, there's going to be a force. Everything is related to these three things. If you're going to remember something from this unit, is these three things. Okay. And so we go to Ampere. It's always weird to pronounce his name in English. In Spanish, it's Ampere. It's very direct, Ampere, Ampere. In English, it's like Ampere, Ampere. I don't know. It's weird pronouncing it in English. We've already referenced Ampere before, right? What are the units for current? What are the units we use for current? Anybody?
Ampere.
Ampere. The ampere is the unit for current. Wow, that's a wow. Why is that, and why is there an Amperes law? Well, Ampere, we call the units for current ampere, and so there's something that's called Amperes Law. Okay, and basically Amperes Law is really something that relates to what we already talked about. So Amperes Law is really related to what we already talked about as the first right-hand rule. Okay, so what does the first right-hand rule say? So again, if we have a current going a certain direction, there's going to be a magnetic field around that current. So when we talked about electrical fields, remember that we had a charged particle, and the electrical field was going to be proportional to the charged particle, to the value of the charge. So the larger the charge, the larger the electric field, and it was going to be inversely proportional to the distance. So the further away we are, the less strong the electric field is. Well, Ampere's law is kind of an analogy to the electrical field well, I'm not going to say law, the electrical field principle that we saw, in the sense that if I have an electrical current that's going through a conductor, I've got this electrical current going here, so any sort of conducting material, that, by the way, can have different geometries. Remember that when we saw an electrical field, we can talk about an electrical field about a point charge, right? That concept doesn't exist in magnetism. Remember that we are always going to have polarity in magnetism. So in electrical terms, we always have a positive or a negative charge that was a point charge. We don't have a point magnetic field. We're always going to have polarity there. So we can have different geometries. So right now we're talking about a conductor. If we have an electrical current going through a conductor, there's going to be a magnetic field that's going to be generated. That magnetic field is going to be proportional to the charges that are moving, that are generating this electrical current. It's also going to have to do with the length of the conductor, which in somehow has to do with the geometry of the conductor that where the current is going through. And the other thing is that magnetic field, this is very important, is going to be radiating in a perpendicular manner, or rather, depending on how you see it, it's going to be going in concentric circles outside of it, and these can be seen as a parallel. The concentric circles are parallel between each other. Remember that the magnetic fields do not intersect. The sum of these times the increment of the distance is going to be equal to the permeability times the current that's going through it. Remember that we had concepts like permittivity when we were talking about electrical charges. Now we have permeability, which is a concept that's similar or analogous, but regarding magnetic fields. So the permeability is this property that we're going to have that's related to how a magnetic field can be generated. So the permeability 0 is the permeability of vacuum, right? Times the current that's flowing, that's going to give us a reference to the magnitude of the magnetic field. And that's basically Amperes law. Now, Amperes law has a lot of applications. So we can have different configurations of this conductor. So the magnetic field that's going to be generated and the forces that are going to be acting there, we already saw they're going to be proportional, or there's going to be a proportionality to the current that's going through the conductor, but also to the length. So remember when we were talking about capacitance, that a capacitance basically, can somebody remind us what are the 3 factors that affect the capacitance of a capacitor?
The distance between the capacitors,
Perfect.
the material.
Perfect.
And
remember the sandwich.
The material.
The material, yes.
The area of the plates.
Area. Perfect. You guys have made me proud, and that's recorded. Yes, so basically a capacitor has 3 components. It's the plaques, and so the area of the plaques, the distance between the plaques, and the material that's called the dielectric that's in the middle. It's basically the sandwich. Now, we already talked about if I want a capacitor that has a very large capacitance, in theory, I would need a very large area, and that's impractical. So what do? We roll up the capacitor, making kind of like a chocorrol, kind of like a gyro there, a wrap, and we compact that. So we can have a very large area in a very small space. Remember that we talked about that. Well, kind of the same principle applies here. So we're talking about the magnetic field. The strength of the magnetic field is going to depend, or going to be proportional to the length of the cable and the current going through it. So for a given current, we would need a very long cable, right, to have a strong magnetic field. So what do we do to make a very long cable or a very long length? What do we do to make it compacted? Well, we roll it up. And that's the concept of a coil. So instead of having one very large cable, we grab that very large cable and we roll it up. It's very important that when we roll it up, there isn't a contact between so there's a space between each of the winds of the coil. And so, again, instead of having a very large cable, we're going to have that same large cable, but it's going to be in a very small space. And so I'm going to be able to generate a larger magnetic field in a very small space. And that's the concept that's derived from Amperes law. That's the concept of a coil. And a coil is going to be this cable that's rolled up around a nucleus. A current is going to be going through it. A current is going to be going through the cable. And that is going to generate a magnetic field. Now, there can be many configurations of these, okay? One that's a very cool configuration is this one inside here. You notice that this is a circle. This is a circle, a closed circle. It's a nucleus, and we're rolling the cable around it. This is called a toroid, which is basically another way of calling a coil or a magnet that has a circular form. And this is going to have a very interesting magnetic field because the magnetic field is going to radiate. It's going to radiate out of here. And it generates a very interesting effect that can be used for example, if I can, that's another thing about coils, the way we're seeing them here. The magnetic field is only going to be there when a current is going through the coil. So what happens if I turn off the current? What's going to happen to the magnetic field if there's no current going through the wire? What happens to the magnetic field?
It disappears, right?
It disappears, right? Correct, Omar. So Again, current going through a wire or cable, that generates a magnetic field. The strength of the magnetic field is going to depend on the length and the current going through. If I turn off the current, there's no magnetic field. So do you notice that I could create a switch? So imagine, this is a donut, right? Imagine, try to use your imagination, and we're going to be doing I'm going to be showing you some videos. Do you see that this is a cylinder here on the bottom? This is a cylinder. Imagine that I place this cylinder that maybe has a magnetic polarity. Imagine that I place it inside the donut. Do you see that? I'm placing the cylinder inside the donut, and there's no magnetic field. Are we okay up to this point? There's no magnetic field. So the cylinder is going to be there, right? Are we okay up to this point? The cylinder is just going to be there. What do you think will happen? And this is a cylinder that also has a polarity, a magnetic polarity. What do you think is going to happen the moment I put current into this donut? What do you think? Just kind of imagine that. Anybody, give me some ideas here. Again, I've got a cylinder that has a certain magnetic polarity, and I'm putting it inside the donut. And right now, the donut doesn't have any sort of magnetic field on it. The donut is my hand. The donut is my hand. And the fingers are the cylinder that has a certain polarity that's going through the donut. What do you think will happen? First off, I don't have any current, so like Omar said, there's no magnetic field. What happens the moment I put current into the toroid? What's going to happen? First off, before thinking about the cylinder, the moment I apply current, what's going to be generated?
Magnetic field.
Magnetic field. Good. What do you think is going to happen to the cylinder once there is a magnetic field around it? Current generates magnetic fields, and magnetic fields generate force. What's going to happen with the cylinder?
It's going to move.
It's going to move. Correct. Thank you, Diana. It's going to move. Because again, with no magnetic field, the cylinder is in place. The moment I generate a magnetic field, and assuming that the cylinder is either a conductive or also has a magnetic polarization, what's going to happen? Either by repulsion or attraction, it's going to move. Does everybody see that? Is that clear to everybody?
Yes.
We're going to actually see if you, I'm trying to make you imagine things. I'm trying to make you think about things and imagine things. Where I'm actually going to show you some videos where what I'm talking about happens. Well, kids, that's the basic principle of any sort of magnetic lock. Do any of you have magnetic locks somewhere in your house, or have seen magnetic locks for doors? The typical and you push it. Have you seen those?
Yes.
The typical in a door where ring me in and push it. Oh, sorry, I didn't push it. And okay, there we go. And you pushed it and it opens. Have you seen those? Have you seen? Have any? Do any of you have maybe? This is a bit more complicated, but maybe you have heaters, or another application of this is magnetic valves. So some boilers or heaters have magnetic valves that open and close for the flow of liquid. These are magnetic, and you can actually hear it click when that happens. It's this concept. It's this concept, and what we're going to talk about, these are called solenoids, different configurations of solenoids. A solenoid is used for these sorts of applications. By turning on or off the magnetic field, I can push or pull a piston. And the other thing is that magnetic fields are strong. Have any of you tried to separate two magnets that are stuck together? Is that easy? Even if they're small magnets, is it easy to separate two magnets that are stuck together? It's not easy. So that's why a magnetic lock, once you lock that with a magnetic field, either by pushing it or pulling it. So a lock can be normally open or normally closed, a switch, so it could be either pushed by the magnetic field or pulled by the magnetic field, it's going to be strong. That's going to be really strong. Okay. And we're gonna see some videos, but this is just one example of applications relating to. Okay, so this concept that's derived from Ampere's law and that gives us these applications, it's hugely important. So going through that principle that an electrical current going through a wire or cable generates a magnetic field that's going to generate a force. If we have different configurations of this, there's so many applications to this that actually a lot of them we have them around us. Okay, but this is a huge concept, which is Amperes law. The other thing that's interesting here is that if we have so we can have different configurations. This is the toroid configuration. We can have. We also have to be careful. Remember that when we talked about coaxial cables, so any sort of cable that we have is going to generate a magnetic field. And so if we have a bunch of electrical equipment, we have to be careful that the magnetic fields or electromagnetic interference doesn't happen. And so that's where things like shielding and other things come about. And the other interesting thing is that, well, if I've got a conductor and I've got a magnetic field and I put another conductor next to it with a current, that's going to generate an effect that has to do with forces, okay? And that can also be used, or applications to this can be generated. And so this is what we have been talked about previously, which is basically the first right-hand rule, okay? That has to do if we have a current going through a conductor, the thumb indicates the direction of the current, and there's going to be current flowing around this. I'm sorry, not current. So there's a current going through the conductor, and we're going to have a magnetic field that's going to be going around it in concentric circles that are going to be parallel to each other. Remember that the magnetic field doesn't cross the magnetic field lines. Okay, so Ampere's law is going to have a lot of very interesting applications that we're going to be talking about. And so talking a little bit more about the different configurations of Ampere's law. So similar to the explanation that we saw on the video, on the YouTube video, about how to calculate the magnetic field for a conductor. This is I'm sorry, for the magnetic field for a wire. Now let's assume that we want to find the magnetic field in any sort of position. And so that's this relationship that we talked about here that has to do with basically the perimeter or the distance that we have. So this concept is important because we're going to have cables, like the example of the coaxial cable, where usually if you look at a coaxial cable, you're going to see the cable here, and then you're going to see a bunch of materials here that generate shielding. Now, why is shielding important? Because we're going to have a current that's going to be moving through this conductor, and that current is going to be generating an electrical and a magnetic fields. And so it's important that these electrical and magnetic fields that are going to be automatically generated here by this cable do not affect other conductors that are around the cable. Because we're gonna see also that if I have a magnetic field going through a cable or a coil, and I put another conductor close to it, I'm gonna induce a current. So magnetic fields, so currents generate magnetic fields and generate forces. However, magnetic fields can also generate currents. So if I have a conductor that has a current going through it, and then I put another conductor close to it, there's going to be a current that's going to be induced. We might not want that to happen. So there's shielding here. And the shielding is also so electromagnetic phenomenon that's around this cable doesn't affect the cable. Okay, and mathematically we can find the relationships between these, the magnetic fields and the permeability and the current using these expressions that we already saw how they can be derived. And basically what we need to remember is that the properties of the material are going to have to do with this, the environment, and that's why the permeability is important, the permeability constant or magnetic constant. Right now we're talking about permeability 0 or for vacuum. The distance, the magnetic field is going to be stronger closer to the current source, and it's going to be weaker outside the current source. And obviously the strength of the current. Those are going to be the factors that are going to affect the magnetic or electromagnetic phenomenon. And so we come to what we were talking about or discussing, this configuration where we have a coil that's very, very useful, that generates this magnetic field that's both inside and outside of the coil, that automatically generates a magnet with a polarity. So we're going to have a magnet with a polarity. This is called an electromagnet. We're automatically going to be generating an artificial magnet or a magnet that's based on electricity. It's an electromagnet that automatically generates a polarity, has a lot of applications, and this is called a solenoid. And we're going to look at some of these applications or discuss some of these applications. We already mentioned that one of the applications can be the movement of a piston or any sort of device that's going to have sort of a linear movement. So there's many applications relating to this concept of a coil that we're going to call a solenoid.